The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to another episode of Stories from Space. I'm your host, Matt Williams, and today we'll be taking a look at the history of astronomy by examining the contributions made by Islamic, Persian, and Indian astronomers, mathematicians, scholars, and philosophers during the Middle Ages. And when it comes to the teaching of the history of astronomy and science in the West, this is an often underappreciated area. In addition to maintaining classical knowledge during the Middle Ages, in which much of this knowledge had been lost to European scholars, astronomers throughout the Arab world and Central and South Asia, they also advanced upon those traditions, and their scholarship would go on to have a profound influence in Renaissance Europe, not the least of which was on a certain Polish astronomer known as Nicholas Copernicus. In fact, one could very easily make the case that Hindu, Arab, and Persian astronomers laid the groundwork for the Copernican revolution, because, as mentioned in a previous episode that looked at the life and times of Copernicus, he did not so much discover the heliocentric model as much as he synthesized the existing knowledge and other earlier heliocentric model concepts into the first comprehensive system. But there were several steps to that revelation. Several breakthroughs and, in particular, challenges to the Ptolemaic model of the universe, and Aristotelian as well, otherwise known as the geocentric model, that needed to be made first. And much like with European astronomers, it came down to challenging certain fundamental dogmas and accepted ideas that did not match up with observations. And of course, it wasn't just classical knowledge that scholars in Asia were responsible for maintaining and advancing, but also their own domestic traditions, which can also be traced back to Mesopotamia and Central Asian traditions that went on to influence the Greeks and Romans and Europeans. As we addressed in a previous episode, the Ptolemaic model was the most widely used and respected astronomical system during the Middle Ages in Europe. The same was true in the Islamic world and Central Asia. Whereas in Europe, it benefited from canonical authority, which viewed Ptolemy's and Aristotle's contributions to astronomy as compatible with Christian teachings. It was similarly viewed with reverence and respect by Islamic, Indian, and Persian astronomers. This should come as no surprise, seeing as how Ptolemy's use of epicycles and equants did predict the motions of the planets with a fair degree of accuracy. And as such, it was used to prepare astrological and astronomical charts well into the 16th century. Still, there were flaws in the Ptolemaic model that drew criticism and revision attempts during the Middle Ages from scholars from the Iberian Peninsula to India. The Ptolemaic model drew criticism due to the complexities arising from it. In particular, not only did every planet require an epicycle revolving on a deterrent and offset by an equant, it also required a different set of these for each planet. And there were still discrepancies between the model's predictions and astronomers' observations by as much as 10%. In addition, astronomers during the Middle Ages throughout Asia and the Middle East drew inspiration from the Surya Siddhanta, an Indian astronomical treatise written between the 4th and the 5th century CE. The name in Sanskrit means sun treatise, and it described the rules for calculating the motion and sizes of the then-known planets relative to various constellations, and also contained orbital calculations of various bodies and even distance estimates. While the distance estimates were highly inaccurate, the treatise also contains estimates on the time it takes for the planets to return to the same spot in the night sky, otherwise known as their sidereal period. For Mars, the treatise assigns a value of 687 days, which is very close to the modern value of 686.98 days. It also estimated the angular size of Mars at 2 arc minutes, or 1/30th of a degree, from which a diameter of 6,070 kilometers, or 3,772 miles, is derived. This is very close to the modern calculated value of Mars's diameter, which is 6,788 kilometers, or 4,218 miles. What's more, this value is thought to have been influenced by Ptolemy's estimate of 1.57 arc minutes, which he attributed to 2nd century BC astronomer Hipparchus. The astronomical tradition of Islamic, Indian, and Persian astronomers also owes a great debt to the Indian mathematician and astronomer Aryabhata, who lived from 476 to 550 CE, and is the author of the 5th century Sanskrit treatise Aryabhatiya. This treatise contained 108 verses written in the style of sutra literature, which are divided into 4 chapters addressing different aspects of cosmology. They include the Giti Kapada, which consists of 13 verses that address the large units of time, including Kalpa, or timelessness, Manvatara, of man or Manu, and Yuga, an epoch. These cosmological periods deal with the time that falls between the creation and recreation of the world, a cyclic period of time dealing with the duration, reign, or age of Manu, the progenitor, and the 4 epochs that follow humanity's moral and physical decline, culminating in a cataclysmic event in rebirth. Second is the Ganitapada, a 33-verse chapter that addresses geometric calculations such as area, length, volume, etc., arithmetic and geometric progressions, and mathematical equations. The Kalakriyapada, a 25-verse chapter, addresses the different units of time and a method for determining the positions of a planet for a given day, and calculations concerning different time organization methods, which include 5 to 6 day weeks, 7-day weeks, and lunar cycles. The last chapter, Golapada, contains 50 verses that deal with the geometric and trigonometric aspects of the heavens, the shape of the earth, the cause of the day-night cycle, or diurnal cycle, and the passage of the constellations through the zodiac. The treatise introduced a number of innovations in terms of mathematics, which allowed Aryabhata to calculate the periods of the planets relative to the sun, the timing of lunar and solar eclipses, and the motion of the moon. He is also renowned for making one of the first recorded proposals that the Earth rotates on its axis, which was his explanation for the cycle of night and day and the rapid rotation of the celestial sphere, otherwise known as the background stars. In this treatise, Aryabhata also offers an early description of the relativity of motion. As he wrote, "Just as a man in a boat moving forward sees the stationary objects on the shore as moving backwards, just so are the stationary stars seen by people on Earth as moving exactly towards the west." This description is reminiscent of Galileo's boat metaphor, which he used to explain how individuals are unaware that they are standing on a rotating body. The Aryabhatiya would have a profound influence on subsequent generations of astronomers from South Asia to North Africa and Europe. By the 10th century CE, many Islamic astronomers were reconsidering the Ptolemaic model of the universe. This included Iranian astronomer al-Siji, whose full name was Abu Sa'id Ahmed ibn Muhammad ibn Abd al-Jalil al-Siji, who lived from 945 to 1020 CE. Al-Siji is noted for accepting that the Earth rotated on its axis as an explanation for the motions of the heavens. According to his contemporary astronomer al-Biruni, who lived from 973 to 1048 CE, this allowed him to invent the astrolabe, which allowed shipwrights to navigate their vessels based on the position of the stars. This invention would find its way to Europe centuries later, which allowed European sailors to colonize the Americas and establish trade routes around the world. Meanwhile, al-Biruni, or Abu Rayyan Muhammad ibn Ahmad al-Biruni, produced volumes on astronomy, many of which address the Aryabhatiya and other works of Indian astronomers. In his treatise, Mishta Ilm al-Hay'a, or Key to Astronomy, he offered updates on the calculations of the circumference of the Earth, which he estimated to be 20,400 Arabic miles in circumference, which works out to 46,614 kilometers, or about 28,965 miles. This is very close to the modern value of 40,075 kilometers, or 24,901 miles. And in his greatest work, Codex Masuni, released in 1031, al-Biruni challenged Ptolemy's claims that the sun's apogee, or its highest point in the sky, was not fixed, but subject to change over time. However, he stopped short on open defiance of Ptolemy's geocentric model and a stationary Earth. despite the fact that a rotating Earth was more consistent with observations. As he wrote in a separate treatise, Tahik ma li il hind, the rotation of the Earth does in no way impair the value of astronomy, as all appearances of an astronomic character can quite as well be explained according to this theory as to the other. There are, however, other reasons which make it impossible. The question is most difficult to solve. The most prominent of both modern and ancient astronomers have deeply studied the question of the moving of the Earth and tried to refute it. We, too, have composed a book on the subject, called Miftah Ilam al-Ha'e, in which we think we have surpassed our predecessors, if not in the words, at all events in the matter. The influence these astronomers and their treatises would have led to the creation of the Maraga Observatory and School of Astronomy in northeastern Iran by the mid-13th century. Several centuries hence, Maraga was considered one of the most advanced scientific institutions in Eurasia, housing a large collection of astronomical instruments and texts, and serving as a center of education where multiple breakthroughs were made. Maraga was also used as a model for later observatories in the Islamic world. This included the Uleg Beg Observatory, founded in 1420 in Samarkand, located in modern-day Uzbekistan, the Taqi al-Din Observatory, founded in 1577 in Constantinople, or modern-day Istanbul, and the Jah Singh Observatory, built in 1737 in Jaipur, India. Meanwhile, the Arab polymath Ibn al-Haytham, or as he was known to European scholars, al-Hazan, released a highly critical treatise between 1025 and 1028 CE, titled Al-Shakuk ala Batlamiyas, which translated means doubt concerning Ptolemy. In an outright fashion, he claimed that Ptolemy's model was a mathematical impossibility and criticized his use of imaginary devices such as the equant, claiming that they failed to satisfy the requirement of uniform circular motion. As he wrote, Ptolemy assumed an arrangement that cannot exist, and the fact that this arrangement produces in his imagination the motions that belong to the planets does not free him from the error he committed in his assumed arrangement, for the existing motions of the planets cannot be the result of an arrangement that is impossible to exist. For a man to imagine a circle in the heavens and to imagine the planet moving in it does not bring about the planet's motion. However, rather than attempting to replace Ptolemy's model completely, he hoped to repair it by finding the true arrangement of the planets and their motions, which he wrote about extensively in his later works. By the 12th century, the Andalusian Arab astronomer Nur ad-Din al-Bitruji, whose Latinized name was Alpetragius, became the first astronomer to break with the Ptolemaic model entirely. Central to al-Bitruji's astronomical model was a theory on celestial motion that did not involve epicycles or eccentrics, and also reintroduced the Greek idea of the motion of homocentric spheres, where the cosmos consisted of concentric spheres, one nested within the other, and the motion of which combined to produce planetary and celestial motions. While al-Bitruji was unsuccessful in resolving the inconsistencies of the Ptolemaic model, his work remained influential throughout Europe and the Islamic world until the 16th century. By the 15th to 16th century in India, astronomer and mathematician Nilakantha Somayaji produced multiple volumes on the motions of the planets in the celestial sphere. One of his most notable works was a commentary on the Arabatiya, known as the Arabatiya Basya. It was here that Somayaji developed a computational system for a partially heliocentric model in which Mercury, Venus, Mars, Jupiter, and Saturn orbit the Sun, which in turn orbits the Earth. This model would influence and predict the system later proposed by Dutch astronomer Tycho Brahe in the late 16th century. In his later treatise, Tantra Sem Graha, released in 1501 CE, Somayaji further revised this system by incorporating Earth's rotation and predicting the heliocentric orbits of the inner planets. While he came rather close, Somayaji never fully embraced or advocated for heliocentrism. Nevertheless, his model would become the accepted model of students at the Kerala School of Astronomy and Mathematics in southern India, a place that played a central role in the development of calculus and predated Isaac Newton's contributions by centuries. The impact and influence of these innovations and revisions would go on to have a profound impact on European astronomers. By the 16th century, the work of Arab, Andalusian, Persian, and Indian astronomers and mathematicians would find their way into European universities and institutions of learning, and would play an integral role in the development of the heliocentric model of the universe. As we covered in the previous episode, the Copernican revolution, it was copies of these translated works, as well as the works of pre-Socratic and Hellenic astronomers, that would influence Copernicus as he studied at the University of Krakow, the University of Bologna, and Padua, that would lead to Copernicus's synthesis, in which he became the first astronomer to introduce a full and complete heliocentric model of the universe, which he described in his seminal work, De Revolutionibus Orbium Celestium, or On the Revolutions of the Heavenly Spheres, in 1543. But of course, the influence of Arab, Indian, and Persian astronomers doesn't end there. In addition to preserving classical knowledge that had been lost to European scholars with the collapse of Rome and the subsequent, quote, Dark Ages, as well as introducing revisions, updates, and challenges to this knowledge, a number of inventions and concepts that made their way from the Middle East to Europe would help spur on the Renaissance and scientific revolution that was taking place by the 15th and 16th centuries. These included, as mentioned, the astrolabe, but also blast furnaces and modern steel, the compass, the windmill, the wheelbarrow, gunpowder, the classification of chemical substances, and alchemy, algebra and many mathematical theorems, and of course, Hindu-Arabic numerals, all of which came from the Middle East, North Africa, Central Asia, and in some cases, from China by way of the Middle East. The influence of Islamic astronomers can also be seen in modern astronomical naming conventions, where many stars still have the Latinized version of Arabic names. This includes, but is not limited to, Achernar, Aldebaran, Betelgeuse, Deneb, Fomalhaut, Jabba, Markab, Megrez, Merak, Saif, Rigel, Spica, Thuba, Vega, and many more. These names live on as part of the International Astronomical Union, or IAU, catalog. In fact, it would not be an exaggeration to say that European astronomers would not have made the impressive strides they had by the time of the Renaissance and scientific revolution, were it not for 1,000 years of contributions, challenges, and innovations made by Islamic and Hindu astronomers, leading up to and throughout the Middle Ages. Join me next time, where we will be taking a look at other non-European astronomical traditions, including the Mayan, Incan, Nechalneth, and Hulkaminam peoples. We'll also be looking at the history of space stations, and a new segment on what it would take to terraform the inner planets of the solar system. And stay tuned for my upcoming interview with Kenneth Goodis Gordon, a physicist and planetary scientist at the University of Central Florida, as we discuss how scientists are developing a new metric for measuring planetary habitability that could be a game changer for future exoplanet studies, astrobiology, and the Habitable Worlds Observatory. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.